I'm diving into Sklearn's factor analysis, a powerful tool for dimensionality reduction. It helps us understand complex datasets by identifying underlying patterns or latent factors. Think of it like finding the hidden ingredients in a complex recipe. This question tests your understanding of factor analysis and its components attribute, specifically when applied to a dataset with 10 features. We'll analyze several statements to figure out which ones correctly describe what components represents. This statement checks if you understand the dimensions of the components array. In factor analysis with 3 components and 10 original features, I expect the result will be a 3 by 10 array. Each row represents a component, latent factor, and each column represents a feature. This is about understanding how factor analysis organizes its results. Each row of the components array describes one of the 3 latent factors that explain the data. I'm checking if you understand this key concept. This gets to the core of what the numbers in the components array mean. Each number represents a loading, showing how strongly each feature relates to each factor. The absolute value tells us the strength of the relationship, ignoring the direction, positive or negative. This tests whether you know what components does not represent. It doesn't give you the reduced data points, instead, it provides the factor loadings. To get the reduced data, you need the transform method. This simply labels the type of model we are using, factor analysis. It's a statistical method for dimensionality reduction. This tells us the input data has 10 features, variables, which factor analysis aims to simplify. I see this statement as correct. Remember, we're using factor analysis with 3 components and a dataset of 10 features. Therefore, the resulting components array will naturally have 3 rows, 1 for each component, and 10 columns, 1 for each feature. Think of it like a matrix showing how much each feature contributes to each of the 3 underlying factors. It's all about the matrix multiplication. This is false. The components attribute doesn't give you the new, reduced dimension data points themselves. Instead, it provides the loadings or the weights that show how much each original feature contributes to each of the 3 new components. To get the actual lower dimensional data, you need to apply a transformation using the transform method on the original data. Think of it like this. Components gives you the recipe, but transform actually cooks the dish. I agree, this is true. Each element in components shows the strength of relationship between a given feature and a particular factor. The larger the absolute value, the stronger the connection. The sign just tells whether that relationship is positive or negative. It's like a scorecard indicating how important each feature is for understanding each underlying factor. I'm going to explain the core idea behind factor analysis, a method to simplify complex data. We'll focus on understanding the meaning of the components attribute in Sklearn's factor analysis. Think of it as a way to find the hidden underlying factors that explain your data. Let's imagine you have a dataset. Each data point has 10 different characteristics, or features. Maybe it's data about houses with 10 features like size, number of bedrooms, location, etc. We use Sklearn, a powerful Python library, to perform factor analysis. We set n_components equals 3 meaning I want to reduce the 10 features into just 3 main factors that capture most of the information. This is the key part. After running factor analysis, the components attribute is a matrix that provides information on how the original 10 features relate to the 3 new factors. The components attribute will be a 3 by 10 numpy array, a table of numbers. 3 rows represent the 3 factors, and 10 columns represent the 10 original features. Each number shows how strongly each original feature is related to each of the 3 new factors. Each of the 3 rows in the array represents one of the 3 underlying factors that we found. The numbers in the array are called loadings. The absolute value, positive value, of each loading shows how strongly each feature relates to the corresponding factor. A larger value means a stronger relationship. I'll explain what the components underscore attribute means in factor analysis. Think of it as a summary of how your original data's features relate to the newly created, smaller set of factors. Each factor is a hidden, underlying variable that explains some of the variability in your data. We're using a tool called Sklearn, a popular Python library for machine learning. Specifically, we're using its factor analysis function to simplify data with 10 original features. The (n_components equals 3 part means we're trying to boil our 10 features down to just 3 underlying factors. This is dimensionality reduction. This is correct. The output of factor analysis's components underscore will be a table, NumPy array, with 3 rows, 1 for each factor, and 10 columns, 1 for each original feature. Absolutely right. Each row of that 3x10 table shows you how strongly each of the 10 original features relates to *1 of the 3 underlying factors. You got it. The numbers in the table show the loadings. The bigger the number, ignoring whether it's positive or negative, the stronger the link between that feature and that factor. Think of it like this: a large number is a strong relationship. A small number is a weak relationship. Nope, that's wrong. (components underscore) just gives you the loadings. It doesn't give you the actual transformed data points. Those data points now represented by only 3 factors. To get the reduced data, you'll need to use a different function, the (transform) method. I'm explaining the meaning of the components attribute in factor analysis. This attribute is super important because it shows you how much each original feature contributes to each newly created factor. Think of it as a map that shows the connections between the old and new variables. We start with 10 different characteristics of something, maybe 10 measurements of different aspects of a flower, like petal length, petal width, sepal length, and so on. We want to simplify these 10 features to only 3 key factors. We're using factor analysis to accomplish this reduction. Components equals 3 tells the algorithm how many factors to create, in this case, 3. The output, components, will be a 3x10 array. Each row represents one of the 3 new factors we've created, and each column represents one of the original 10 features. The numbers in the array show the strength of the relationship between each factor and each feature. I'll explain what the components underscore attribute means in factor analysis. Think of it as a summary of how your original 10 features relate to 3 newly discovered underlying factors. We start with data having 10 different characteristics or features. For example, if we're analyzing houses, these could be things like size, number of bedrooms, location, etc. We're using a tool from Sklearn called FactorAnalysis to simplify the data. I've told the tool to find 3 underlying factors that explain the relationships between the 10 features. This reduces the complexity, allowing you to view trends easier. The components underscore attribute is a table, a NumPy array, showing how strong the relationship is between each original feature and each of the 3 new factors. The table's size is 3 rows, 1 for each factor, and 10 columns, 1 for each original feature. Each row in the table represents one of the 3 newly discovered factors. These aren't directly observable but represent underlying influences on the original features. Each column represents one of the original 10 features. Each number in the table is a loading. It indicates how much each original feature contributes to each underlying factor. We use the absolute value, which ignores whether the contribution is positive or negative. A bigger number means a stronger relationship.